Now you can go to Claude or whatever and vibe code something. It's not that far of an analogy to say this is how physical robots are acting. However, the same kind of limits do apply. You can get to a level of complexity, but could you build a full humanoid that folds your laundry and walks around the house and takes the dog out and drives the kids to daycare? Not yet.
Yeah, but we're getting there.
I actually view location as not like this alternative, if you will. It's like, it's an amplifier to all of these capabilities that people are doing. It's another sensor, is another way to think of it. The analogy works for humans too. I mean, we've talked about this where like, if you are lost in a city and you don't have GPS, or if you've been driving long enough, you don't have paper maps, like you're kind of like, okay, I got to pull over and ask someone for directions. Maps are really powerful shortcuts to make it so that you can actually do local intelligence, but have a globally like optimum trajectory or whatever it is that you're optimizing for.
So let's just start off at a top level, Aaron, and how do you think about physical AI and how would you describe it?
The way I think of it is that when you think about computing in general, most computing exists in the context of digital only world. So you think of a traditional database like your Postgres or something. It's pretty deterministic. You write commands, it does what you say, and the world basically reflects what we digitally expect to happen. The physical world is far less deterministic, much more complicated, and everything is in the context of kind of probabilities and statistics and uncertainty. And so what I think about when we talk about physical AI is actually systems that influence the physical world or represent the physical world that we are interacting with digitally. So, I mean, the easiest example of that is like a map is an example of physical AI, and then being able to do something with that map, like reason about what's the fastest way to deliver a set of packages. That, in my mind, encompasses part of physical AI. One that gets the most press is robotics, and I think it's important to remember that it really what makes it so different is the world that we live in being fixed. It's the digital world is one that we designed. The physical world is one that we were just brought into. We have to deal with. So that's it.
Yeah, so you touched on something there that we literally, I think it was 30 minutes ago, we're just having a chat, and I'd asked you the question then was, it seems that, at least based on some of our previous conversations and stuff I've looked at, that all robotics now is physical AI, or in some way is using physical AI and be thought of as physical AI, which again has the danger of it's everything and it's nothing. But you also touched on, and do explain that a little bit more, in your mind, it's not just robotics, the physical things that are interacting with the real world. It's also digital solutions or digital products. Well, then give me an example of that, if you would.
Yeah, I mean, there's lots of them. So like probably the one that we've all worked with is like a rideshare system. There's a problem, digital, that has to happen where I have a fleet of drivers. I have a bunch of people who want to get places. How do I decide like which drivers meet which people? And then by having a digital system do something, I'm making a physical action happen in the real world. The guy's driving up with his car, picking someone up from the airport and taking him home, right? So there's in my mind, it's not super important whether the thing influencing the world is like a motor or a human. Like it is, that is just the action part of the equation. The physical AI part is how do you do all that sensing, reasoning, digitization that happens kind of in that control layer. Like that's actually when my mind makes it physical AI.
But there is a key characteristic about a physical AI system, let me call it, that is wildly different than a digital AI system.
Yeah.
And let's dig into that, because that may be what we can anchor on.
Yeah, absolutely. So digital AIs or, traditional AIs, I guess you could call them, are the things that, I think a lot of people now have experience, with ChatGPT and other
And I can't
LLMs and
believe you
stuff.
said traditional AI
I
for
know, right?
ChatGPT. It's so crazy.
Here we are.
Yeah.
And I mean, yeah, these things didn't exist at scale too long ago. But those things now, I mean, they're pervasive. And, they came on incredibly rapidly because the digital world was already pretty well organized, thanks to the internet and everybody contributing content to that and digitizing even analog content like books and everything from
Mhm.
basically the entirety of human knowledge. Almost entirely exists on the internet. So it makes sense that you were able to take these kinds of algorithms that just feed on data and output reasoning. They were able to go very quickly, take all the digital knowledge and convert it now into something that resembles intelligence. And so now we're in the second chapter of what about interacting with and understanding the physical world
Mhm.
that is not yet fully digitized and certainly not in real time. And so you see these kind of almost point solutions starting happening where you may see an amazing demo of like a Boston Dynamics Atlas robot or something. It's really good at knowing like the context around it, but it probably doesn't have huge knowledge about the whole rest of the world and everything that happened. And so there's a bunch of really amazing techniques that people are using to either simulate or emulate the learning part of that, but it is fundamentally, in my mind, a much harder problem because the physical world is one that, like, we all are programmed as living beings to understand, like, what to expect next. And when it doesn't quite look right, it doesn't work. I mean, you even see it in some of these AIs that are doing things like trying to make videos and like something doesn't quite look right. That is kind of where you start to see that blurring of the lines.
Yeah, and so if we continue, let's continue on this a little bit
Yeah.
more, looking at the nature of the physical world, where you're trying to ensure that the thing, whether it's just a digital, like the software that you talked about, or let's actually bring it into robotics a bit, which is that thing's dealing in probabilities. Like
Yeah.
deterministic on the software side is pretty straightforward. Now you have systems that are trying to figure out what it sees and
Yeah.
interpret what it sees, and that might be the kind of one of the crux things that we can say that is physical AI potentially.
Yeah.
Is this, and I forget the cycle that you have used before, where you sense something, you learn, and then you act, or
Act. Yeah.
something like that.
Yeah. And I mean, that's been the, canonical definition of robotics for a long time, the, sense, learn, act kind of loop that happens. Um, and I think what's really fascinating is these models, these like data driven algorithms. The previous way that robotics used to work was that, really smart folks would derive physics and kinematics and all these other, things. And we would use that knowledge to kind of like, take like a traditional robot, like an assembly robot in a,
Mhm.
automotive plant. You could deterministically be like, okay, these are going to be the joints of the arm, and I'm going to pick up this giant piece of metal and put it exactly here. Um, Amazing stuff, but it is entirely programmed by experts. And so that robot has no ability to deal with what inevitably happens, where the real world and the expectation of the real world have a gap.
Yeah,
So,
and things are moving in its sphere of influence as
yes.
well,
And
which in that scenario that you mentioned, like nothing gets near that robot.
yes, it is literally in a cage
Yeah,
because it's like, I mean, it uh, doesn't perceive, fear
yeah.
or any kind of those things. Now, what's amazing is with these new systems, they are able to have more context about what's going on around them. And so you can see like it turns out like gripping, like literally figuring out how do I like bring a hand and like pick something up is one of the hardest, problems, especially when you're talking about uh things that are not rigid. So you can think about like, how do I pick up like a hacky sack or like,
Yeah.
an egg or something? Um, and so, this is something where traditionally we'd use like controls methods, which again, rooted in physics, required lots of experts to kind of design. Now you're coming at this from like a data problem where you could effectively like teach a model, and there's a whole argument on a different plane of like, do we just do a bunch of teleoperation? Do we just watch humans do it a lot? And that's a whole other body of research. But the core of it is that if you can give these systems enough data, they actually are able to more or less back out how the physics works. So they don't need to have years of knowledge of how control theory works and everything. They effectively are just able to predict what the world's going to do by looking at how it's reacted in the past, and then say, okay, I am going to come up with a strategy to simulate picking up this cup, and I'm going to do it successfully, and
Yeah, yeah.
eventually also get better at it, which that's the kind of holy grail. Um, so similar to how traditional computer programs used to be a bunch of really expert programmers would write something and be very deterministic and work the same way every time. Now you can go to Claude or whatever and kind of vibe code something. Um, it's not that far of an analogy to say this is how physical robots are acting. However, the same kind of limits do apply, where you can get to a level of complexity. But could you build a full humanoid that folds your laundry and walks around the house and takes the dog out and drives the kids to daycare? Not yet.
Yeah,
So,
yeah, yeah, yeah. But we're getting there. We're
yeah,
seeing
yeah,
more and more of that. Cool. So one of the things that you touched on that I always found when I came into the industry, this industry, which was enlightening. I mean, it's basic for folks like you that have been in it forever and seen the days of $10,000 sensors, is kind of this enabling of physical AI. A lot of that has to do with just purely the cost and availability of these incredibly powerful sensors and the ability to pull all that information together at incredible speed.
yeah,
And I think it started either with phone or cars or
yeah.
one or both.
Yeah, I mean, I think phones to start, and now cars. We're seeing that curve come down. In a lot of ways, it's kind of phones are these amazing things because before anybody said physical AI or literally anybody was seriously talking about robotics, except a bunch of crazy people like me back in college, um, the phone is actually the first kind of thing that connected that physical and digital world. I gave the example of rideshare. If you think about like the thing that had to happen to make ride sharing work was the phone had to have GPS and
Mhm.
connectivity. And with those two ingredients, all of a sudden it was like, wait a second, I can like now have this digital real-time representation of what the world looks like and connect the dots. So now I can very efficiently use an algorithm to connect a driver to a passenger. And so that's like, in my mind, like the very first real, like a scaled consumer application that we saw of this physical and digital worlds coming together. Um, and the insane part about this is that phones have pushed the envelope of compute, of sensor technology. I don't even remember how many megapixels are in the latest cameras. And it's like, to think about what a digital camera was, you know, in the early days to now,
Yeah,
I mean,
yeah,
it's
yeah.
it's unbelievable. So there's all of that resolution, all of that compute, all of that bandwidth all translates to higher fidelity that now we can build
Yeah.
systems that operate in that digital and physical world at the same time. And so, yeah, it's kind of a wild thing to think that the computer in my pocket has been a key enabler to what will eventually be these, robotic systems that we just live with every day.
Yeah, and then you've got lidars, which used to be prohibitively expensive. I mean,
Yeah,
it'd actually be interesting to know how you actually outfitted your first, what your first physical AI project was many years ago in the DARPA challenge. Maybe we'll cover that off someday. It's
yeah,
probably rather extraordinary in your brain, which now is these piece parts that cost $10 or $30. But yeah, so lidar
yep,
technology has really, really come down. In addition to other sensors
yeah,
that are critical for
yeah.
physical AI.
And I think one of the exciting things is, LiDAR is interesting because it's a direct measurement sensor. Like it literally just tells you off the sensor physically, like this is the distance to a point. Um, what's I think really fascinating is what you see happening with cameras, where people are just bypassing. There used to be all these algorithms and geometries and very careful calibration that happened. And a lot of the latest systems are just full end to end, where they're connecting a camera to an actuator, and they have a network in between. And the things that they're able to do, I mean, are shocking. And I think that's, it just goes to show that um, for a sufficiently reasonable context window, you can actually build incredibly capable AI systems. We haven't yet solved the like general long horizon problem, but I do think that there's uh, a huge capability unlock that has happened in terms of taking what are very simple basic sensors like
Hmm.
imagers
Hmm.
and turning that into like, oh, I actually understand what the world means, even if we can't introspect it. So
So, part of this too is, so we're in a world, as you're talking, we're in a world where actually physical AI, it sounds like, has been around for a while. We have many industries that have been embedding more and more sophisticated capabilities, including automated lawnmowers now
yep.
that are out, and now some of those have LiDAR on them as well. Many or most use cameras as well. And uh, so the kind of the frontier on the hardware and sensor side seems like it has been progressing very, very, very quickly.
Yeah.
And in many instances, we can think about these technologies as being pretty ubiquitous. But there's a part of this solution, though, that we chat about a lot, that is still, in some senses, wildly fragmented, and that's the context layer.
Yeah.
And especially if you look at indoor and outdoor, and let's just start at a meta level about, okay, so we talked about sensors, robotics, but now we have the context layer for those things,
Yep.
and start at the top, just like maps and indoor versus outdoor.
Yeah. I think this is a really important point because when we talk about the capabilities of these systems, they're able to do what are fairly well defined tasks pretty amazingly well. But it's that like chaining together part, doing them over like a longer horizon, doing it in a way that's actually useful, like in a warehouse or something. That's still really challenging. And basically, what the companies that are successful doing this, what they are having to do is build effectively their own maps. So if
Hmm.
you're
Hmm.
operating in a warehouse, it's like most of them come in, there's some process that happens, and they have to build basically a map of, okay, here's where the aisles are, here's where the shelves are. The robot may have a lot of intelligence of like, let's imagine it's a forklift. How do I, perfectly, go and get that pallet on, the actual fork and bring it up and do all the crazy physics required to not tip over, but like um, the actual path planning and like how do I figure out where I'm going in the context of a warehouse still is challenging. And so when you look at outdoors, I think that you see a lot more capability there. And I mean, candidly, that's because the outdoor location problem has a really nice solution, which is to use satellites, GPS. And, our company and others in the space, we've created a capability where now you can get to centimeters there. So what happens is that the robot can be concerned with, okay, what do I need to do once I know where I am? And that's a much, much simpler problem than just saying like, get rid of all the weeds on this field, like, and so, and it lets you also have superpowers. So for instance, you can do things where you can't actually perceive the element that you're trying to manipulate. So concrete example, I could plant a seed and never see that seed, but I could remember where I planted
Hmm.
it and then apply specifically like water, fertilizers, whatever, exactly on that spot, not the whole field. And now I saved a bunch of money and reduced, waste and all these good things. And so I actually view location as not like this alternative, if you will. It's like it's an amplifier to all of these capabilities that people are doing. It's another sensor, is another way to think of it.
Yeah.
And the analogy works for humans too. I mean, we've talked about this where like if you are lost in a city and you don't have GPS, or if you've been driving long enough, you don't have paper maps, like you're kind of like, okay, I got to pull over and ask someone for
Yeah.
directions,
Yeah. Yeah.
and so maps are really powerful shortcuts to make it so that you can actually do local intelligence, but have a globally like optimum trajectory or whatever it is that you're optimizing for.
Yeah, and so when you stick on outdoors just for a minute too, I think
Yeah.
one of the other fascinating things that you've mentioned before is that we actually have a common coordinate system outdoors, if you will.
Yes.
Like we have lat long,
Yes.
and so for the most part, lat long isn't always my lat long's not always your lat long, but they're pretty darn close.
Yes.
Indoors, getting back to that challenge is different.
Yeah.
And everybody, again, getting back to this fragmented nature, if you have three different systems inside of a warehouse, you're going to have three different maps of the inside, and those, just call them robots or
Yeah.
devices or whatever they are, being able to interact in a common plane like you can outdoors just really doesn't exist yet today.
Yeah, and I think part of it is the maturity of where we're at. The multi-agent problem, as I call it, where, if you think about like what are the things that these robotic systems can do that we can't. Well, one of them is that they can have perfect real-time communication. Like I can send a TCP packet from one robot to another. Um, and so you can think about, again, going back to that like invisible sensor concept. Sure, I could have like an entirely reactive set of autonomous forklifts in my warehouse, and they're all just using their lidars to not hit each other. But it turns out it's way more efficient if they all know where each other are and they're able to kind of have that like. I'm sure we all kind of seen this animation before where you have a city with no stoplights, right? It's just everything is automatically instantly coordinated. It turns out this is actually how like Kiva Systems, which was the company Amazon bought a million years ago to do their moving shelves in their warehouses.
Hmm. Hmm.
Basically how it works. They have like a global view of what's happening, and they can very quickly manipulate and operate in the world without having to necessarily perceive each other. Um, I'm not saying you do one over the other. I'm saying why not do both,
Yeah,
and
yeah,
then
yeah.
you can have a far more optimal system. And that's like if you have a homogeneous fleet, what's really cool, and if you believe in like the full robot maximalist view, these warehouses are going to have 20 whatever different vendors of all kinds of different robots moving around, from I don't know, forklifts to drones to who knows what. And like you want all of them to be able to do this, have this superpower, so it necessitates effectively a common frame that they can all operate
Yeah,
in.
yeah.
And yeah, I mean, to me, I'm like, the obvious solution is just use the same thing that's outside because it works and everybody agrees on it. So,
There are a lot of applications that are indoor and outdoor.
yes.
It's not either or. We have airports and we have ports and we have warehouses and
Yeah.
we have all kinds of areas that have this back and forth. And today you switch from we have these customers, they switch from their GNSS based solution when they're outside and they're perfectly happy. And then the moment they go underground inside the airport, it's a completely different solution.
Yeah.
And the time and cost associated with that is just, I mean, I would say it's ridiculous, but we're injecting so much extra time and cost that we don't need to.
Yeah. And I mean, also from a deployment perspective, one of the barriers becomes, okay, well, to start my robotic thing, I have to have a map or whatever it is of the place. And that's friction. If you could just have the map, then all of a sudden it's like, okay, cool. We can bring up any robots that's built on this kind of open framework. And I
Mhm.
think that's we see it in agriculture today, where you have all ththese different, I mean, I have to admit, I did not know as a sliver of the sliver I know now of how many different things there are on a farm in terms of implements and tractors and,
Yeah.
even just static sensors and drones and everything. And they all work in this beautiful dance. And, there's tons of companies that have built data layers that sit on top of all of those different robots and sensors to have farmers make the right decision about what to plant, where to put pesticides, whatever the case may be. And I think that analogy, there is no reason that can't extend into construction, into mining, into autonomous driving, frankly, and then warehouse logistics. And I mean, I always say this: it's anything that moves. Like I think that
Yeah.
you can coordinate like that whole world. So
Yeah, and maybe the last thing on this, and we'll get to questions, is it's actually one of the things that I find interesting is that even in the outdoor world, outdoor actually works like indoor as well frequently, right? When you're in a big city,
yes,
you're for all intents and purposes, you're inside.
yeah.
So we're faced with this problem even in the outside world. So um, thanks so much, Aaron.
Thank you, Tom.
It was great, this new setup. I hope this worked really well. And we'll take some questions. I'll see if there's anything coming through here. Next week is the 10th anniversary of Point One. What has been the best and most challenging parts of the journey? Yeah, why don't I leave it there? Or, or anything you want to say about Point One and 10 years being here.
So not the move.
Yeah, and
Okay.
it's certainly not the move because this is a disaster.
Yeah.
Not a disaster.
No, it's not. um, yeah, I think that one of the hard things with our business in general is we build for the future, and I think timing is a really hard
Mhm.
thing.
Yeah.
And so we obviously have a very opinionated view of what the future looks like. And I think a lot of people agree with us, but getting to scale is obviously a much more challenging thing than just getting people to agree with you. And I think it took us many years to get that scale, and like we've made huge strides now. Where I think the industry has finally got to a point where people understand a lot of what we were saying in the beginning of there's a need for globally consistent location. If we can get you centimeter level accuracy, that's not just useful, but it's like existential to a lot of these use
Yeah.
cases working. And there was a lot of folks in the beginning that were like, "Well, we can do it, some other way," and that's all true. What our position always was that these things are not mutually exclusive of each other. There is always more information if we are able to fuse those different sources together.
Mhm,
And
mhm.
so I think that has been a challenge for us to get people to understand or agree with, I guess, in the early days. And now I think the technology, the market has become pretty surely convinced at this point that this is a not just useful, but like literally it's a enabling technology. And I mean, candidly, the price points of doing it and everything have supported that. So then
Yeah,
now
yeah,
it's
yeah.
consumer.
Yeah, yeah, yeah,
Um,
yeah. And as we've been talking about today, there's so much, or there seems to be this consistent newness and new frontiers to break
yes.
down, including this indoor-outdoor challenge, which we're constantly looking at ways we can just bring high accuracy to the world.
Yeah.
Um, okay, let me grab. Um, Slam. So talk about Slam a little bit too,
Yeah.
and then in the context of maybe using Slam on its own
Hmm.
when you're in a world where things are shifting, take a warehouse, things moving
Yeah.
around, other things. Yeah. So let hit on that topic.
Yeah, for sure. So, I mean, first of all, SLAM is simultaneous localization and mapping, just to expand the acronym. And the general concept is, I think, pretty clear, where you're basically trying to build a map while you are moving around and figuring out where you are in that map. So it's,
Thus
you know,
simultaneous.
that's the simultaneous
Okay.
part, right? So
Smart.
it is. So the point of this is that it allows you to go into these unrehearsed scenarios, like places where you don't have a prior map, and you can do clever things like look at if you come back on the trajectory that you started on. There's a whole technique called loop closures, which basically let you cancel out like accumulated errors that you might have over time. And it's a really powerful technology that's been around for a long time. I mean, even back in the DARPA Grand Challenge days, people were, experimenting with SLAM in the robotics lab. And I think it's a very important concept. The trick with SLAM is that by default, it is an entirely relative navigation scheme. So you start up your robot or whatever, it's at 0, 0. And then, like, in the most simple case, you can think of a robot that's got two wheels and a LiDAR on it. And effectively, all it's doing is thinking about how am I moving and how do the scans of the walls kind of move as I'm moving. You can kind of think about it like they move inversely to how I should be moving. And so if I accumulate those deltas over time, they both give me information about my location, about how I've moved in that frame. but it doesn't tell you anything about your global position. So now if I have multiple robots that I'm trying to have operate, I don't have that global context. There are tricks and, multi-agent slam, yes, it's a thing, but like it is, uh, it is, I think, most useful as a tool to build what are effectively like a relative navigation system. Now, you can also decouple SLAM, where you can use SLAM to actually just build the map. And this is something that we think is very powerful because the first time you go to a place, you definition won't have a
Mhm.
map. So you have to do something. And so the idea is, okay, we're going to run basically a SLAM pipeline, and we can actually have, let's say it's a human walking around with a sensor. You can even coach them to like do it in a way that's going to be really good for that algorithm to converge, but then you have the map. And the key is that de-simultaneousizing, that's a word. the localization and the mapping process allow you to actually have a lot more richness in that map, and importantly, allow you to bring in other things like, let's imagine you do have RTK GPS in some of the cases where you're doing that process. Now you can actually anchor that map in global
Right.
frame.
Yeah. Yeah.
And so there's a lot of really cool things that happen when you uh, take the raw concept of SLAM, but like integrate it into a greater system. And I think, this is a lot easier said than done. There's a million ways it goes wrong. It's very different from LiDAR to camera. So each modality of sensing like works a little differently. Um, and so, yeah, I mean, I'd say most robotic systems today use some form of SLAM for indoor, especially localization. But yeah, there's a lot of different ways to skin that cat.
Excellent, excellent. So last question, sticking on the on maybe SLAM as part of this as well, which is getting very specific about the, let's call it the threshold between indoor and outdoor, and just like practically, what are the indoor techno, like what is that handoff, and what are robotics companies actually doing
Yeah.
today to facilitate this moving back, and what does it have to do?
Yeah, it's hard because really what you're trying to do is align two different coordinate systems, and there's a lot of ways that goes wrong. So going back to SLAM, let's imagine we built the map the way I was saying before. Well, you may have some what's called integration drift when you built your map. So what happens is, imagine, let's say you have a perfectly square building that you're driving in. Well, it turns out that when you mapped it, it kind of got a little bit twisted. So now let's imagine there's two doors on this square building. When you come in door A, you drive around a bit, put a pallet on the shelf, whatever it is, and then you come out door B. Even though you kind of shifted your slam based map to like some latitude and longitude, the map itself can actually have distortions. It's kind of like a twisted, I don't know, print in a 3D printer or something, right? It's that distortion ultimately means now that I need to not just like align this local SLAM map that I created, but I actually need to kind of stretch it into the canvas that is the global frame. Uh, that is all really hard to
Yeah.
do correctly, especially when we're talking about like centimeter level type of accuracy. And so, there are definitely like techniques to do this, and there are mathematically rigorous ones that are harder. There are less sophisticated ones that like maybe work good enough for some cases. And the point is that like if you're building like a whole robotic system, like yeah, you're gonna have to make a lot of those trades because you've got a million other problems. What I see happening is that more companies are figuring out how do we solve that problem generically and then make it useful for everyone. And I think that's going to be the future
Yeah.
for sure.
Yeah. Excellent. Thanks so much, everybody. Really appreciate you joining us again today, and thank you, Aaron, as always.
I'm happy to
I
do it.
I learn so much even in these conversations. It's an awesome role I have here to interview you. So, hope you can join us on the next one. We'll be 2 or 3 weeks. We'll be back, and you all have a great day.
Thank you.